So, here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're wrapped in a blanket of air that stretches about 100 kilometers above your head. And that air, that thin, invisible shell around the planet, is the only reason you're alive. It's the reason water flows instead of boiling away. It's the reason your skin isn't being shredded by cosmic radiation. It's the reason the temperature outside isn't swinging from 200 degrees below zero in the shade to over 100 above in the sun, the way it does on the moon. And for most of human history, nobody really thought about it. The air was just there, like the ground, like the sky. You breathed it, you felt the wind, you watched the clouds roll in, and that was about as far as it went. But a few people, a surprisingly small number of people actually, started asking questions about it. Not just what the weather would do tomorrow, but something deeper, something stranger. They wanted to know why the earth is warm at all. Why is it the temperature it is, and not some other temperature? What controls that? And the answers they found, slowly, over centuries, built into one of the most important stories in all of science. It's the story of how we figured out what our atmosphere actually does, how it shapes the climate, and eventually, how we realized we were changing it. That story starts a lot further back than you might expect. Let's go to ancient Greece for a moment. Around 340 BC, Aristotle wrote a book called Meteorologica. And the title might sound familiar because it's where we get the word meteorology. But Aristotle wasn't doing meteorology the way we'd recognize it. He was trying to explain everything that happened between the surface of the earth and the sphere of the moon: rain, wind, thunder, earthquakes, comets, the Milky Way. He lumped it all together, and his explanations were mostly wrong, honestly. He thought the earth gave off two kinds of exhalation, a wet one and a dry one, and that these exhalations, mixing in different ways, produced all weather phenomena. Rain was the wet exhalation condensing. Thunder was the dry exhalation getting trapped in clouds and bursting out. Now, none of that holds up. But here's what's interesting about Aristotle's approach. He was trying to build a physical theory of the atmosphere. He was saying, look, these aren't random acts of the gods. There are natural causes. There are mechanisms. And that idea, that the atmosphere operates by physical rules that humans can understand, that's the seed of everything that comes later. It took a very long time for that seed to grow, but it was planted right there, in the 4th century BC. For about 2,000 years after Aristotle, progress on understanding the atmosphere was slow, really slow. People could observe the weather, they could notice patterns. Sailors knew about trade winds, farmers knew about seasonal rains. But the tools to actually measure what the atmosphere was doing simply didn't exist. You can't study air pressure if you don't have a barometer. You can't track temperature changes if you don't have a thermometer, and those instruments didn't arrive until the 1600s. Galileo gets partial credit for the thermometer around 1593, though his version, called a thermoscope, didn't have a standardized scale. It could tell you that today was warmer than yesterday, but it couldn't give you a number that someone in another city could compare to their own reading. The mercury thermometer, the kind that actually lets you do real science, didn't come along until Daniel Gabriel Fahrenheit developed it in the early 1700s. And the barometer, the instrument that measures air pressure, was invented by Evangelista Torricelli in 1643. Torricelli was a student of Galileo's, actually, and he figured out that if you filled a glass tube with mercury, sealed one end, and flipped it upside down into a dish of mercury, The mercury in the tube would drop to a certain height and stop. The space above it was a vacuum, and the height of the mercury column told you how much pressure the atmosphere was exerting on the dish. That was a revelation. It proved that air had weight, that the atmosphere was pressing down on everything all the time with a measurable force. Think about what that meant. For the first time, people could quantify something about the air around them. It wasn't just wind and weather anymore. It was a physical substance with mass and pressure, and it could be measured. That's the moment atmospheric science becomes possible. But understanding the climate, not just the weather on a given day, but the long-term patterns that make the tropics hot and the poles cold and the temperate zones livable, that required a different kind of question. And the person who arguably asked that question first, in a way that really matters to our story, was a French mathematician named Joseph Fourier. Fourier is one of those figures who shows up in so many different branches of science that it's hard to keep track of him. If you've ever taken a physics or engineering course, you've probably encountered Fourier transforms or Fourier series, mathematical tools that are used everywhere from signal processing to quantum mechanics to audio compression. The MP3 files on your phone rely on math that Fourier developed. But before he became famous for his mathematics, Fourier had a fascinating life that shaped everything about how he thought. He was born in 1768 in Auxerre, France, the son of a tailor. Orphaned by age 9, educated by Benedictine monks who noticed he was extraordinarily gifted in mathematics. He got swept up in the French Revolution, literally. He was arrested twice, once by each side, and narrowly avoided the guillotine. Then Napoleon took him to Egypt in 1798 as part of the scientific expedition that accompanied the military campaign. Fourier spent 3 years in Egypt, and he became obsessed with heat. Some historians think the Egyptian climate itself had something to do with it. Here was this Frenchman from a temperate climate, suddenly immersed in desert heat, and he started thinking deeply about what makes one place hot and another cold. When he got back to France, Fourier threw himself into the study of heat conduction, how heat moves through solid objects, and he developed a mathematical framework for it that was genuinely revolutionary. His 1822 book, Théorie analytique de la chaleur, The Analytical Theory of Heat, is one of the landmark works in the history of physics. Lord Kelvin later called it a great mathematical poem. But here's where Fourier connects to our story about climate. While working on heat, Fourier asked a deceptively simple question. Why is the Earth as warm as it is? He knew from basic physics how much energy the Earth receives from the sun, and he did a calculation, a rough one, but a calculation, of what the Earth's temperature should be if it were just a bare rock in space, absorbing sunlight and radiating heat back out, and the answer he got was too cold, significantly too cold. The Earth, according to his math, should be a frozen ball. But obviously, it wasn't. So something else had to be going on. Something was keeping the Earth warmer than sunlight alone could explain. Fourier published his thoughts on this in the 1820s in a series of papers, and he proposed that the atmosphere itself was acting as a kind of insulating layer. He compared it, and this is a famous analogy, to a glass box. If you put a thermometer inside a glass box and set it in the sun, it gets hotter inside the box than outside. The glass lets sunlight in, but traps some of the heat. Fourier suggested the atmosphere was doing something similar for the entire planet. Now, Fourier's understanding of the mechanism wasn't quite right. He thought the atmosphere worked mostly by preventing warm air from rising and escaping, which is actually closer to how a real greenhouse works, by suppressing convection. The actual mechanism, which we'll get to, involves the absorption and re-emission of infrared radiation, which is a different process. But Fourier identified the core puzzle. The Earth is warmer than it should be based on solar input alone, and the atmosphere is responsible. That insight, published almost 200 years ago, is the foundation stone of climate science. And here's what I love about this. Fourier wasn't trying to study climate change. He wasn't worried about industrial emissions or global warming. He was a mathematician trying to understand heat. He stumbled into one of the most important questions in earth science almost by accident, because he followed the math where it led him, and the math said something was missing. So the question was on the table. The atmosphere traps heat. But how? What part of the atmosphere does it? And by what mechanism? Fourier didn't have the tools to answer that, but someone else would, and she would do it with a remarkably simple experiment. In 1856, an American woman named Eunice Newton Foote presented a paper at the annual meeting of the American Association for the Advancement of Science. Actually, and this detail matters, she didn't present it herself. A male colleague, Professor Joseph Henry, read it on her behalf because women weren't typically allowed to present their own work at scientific meetings in the 1850s. The paper was titled Circumstances Affecting the Heat of the Sun's Rays, and it described an experiment that was elegant in its simplicity. Foote took glass cylinders, filled them with different gases, put thermometers inside, and set them in the sun. She tested regular air, hydrogen, and carbon dioxide, which she called carbonic acid gas, as it was known at the time. And what she found was that the cylinder filled with carbon dioxide got significantly hotter than the others, and it took much longer to cool down once she moved it out of the sun. Her conclusion was direct and clear. She wrote that an atmosphere of carbon dioxide would give to our Earth a high temperature. She even speculated that if the atmosphere had contained more carbon dioxide in the past, it could explain why earlier geological periods had been warmer. Think about that for a second. In 1856, 3 years before Darwin published On the Origin of Species, an American woman who was largely self-taught in science identified carbon dioxide as a heat-trapping gas and connected it to Earth's climate history. And then, she was almost completely forgotten. For over a century, the credit for discovering the heat-trapping properties of carbon dioxide went to someone else, an Irish physicist named John Tyndall, who published his own, more detailed experiments in 1859 and the years that followed. Now, Tyndall's work was extraordinary, and we should talk about it, because he went much further than Foote, and his methods were more rigorous. But Foote got there first, with a simpler experiment, and the fact that her contribution was overlooked for so long tells you something about who got to be part of the scientific conversation in the 19th century, and who didn't. Tyndall was a character. Born in 1820 in County Carlow, Ireland, the son of a local police constable, he worked as a surveyor and a draftsman before finding his way into science, eventually becoming a professor at the Royal Institution in London, one of the most prestigious scientific posts in the world. He was also a mountaineer. He made the first ascent of the Weisshorn in the Swiss Alps in 1861, and he had this incredible ability to design experiments that isolated exactly the variable he wanted to study. What Tyndall did, starting in 1859, was build an apparatus that could measure how different gases absorbed radiant heat, not sunlight specifically, but infrared radiation, the kind of heat energy that warm objects emit. And this distinction is crucial, because it gets to the heart of how the atmosphere actually warms the planet. The sun sends energy to Earth mostly as visible light. That light passes through the atmosphere pretty easily. The atmosphere is largely transparent to visible light. The sunlight hits the ground, warms it up, and the warm ground emits energy back upward. But it emits that energy not as visible light, but as infrared radiation, which has a longer wavelength. And here's the key. Certain gases in the atmosphere absorb infrared radiation very effectively. They catch that outgoing heat and re-emit it in all directions, including back down toward the surface. That's what actually warms the planet beyond what sunlight alone would do. Tyndall tested gas after gas. Oxygen and nitrogen, the two gases that make up about 99% of the atmosphere, turned out to be almost completely transparent to infrared radiation. They don't absorb it at all. But water vapor, carbon dioxide, methane, and a few other trace gases absorbed it powerfully. Tyndall was astonished by water vapor in particular. He called it a blanket more necessary to the vegetable life of England than clothing is to man. He recognized that without these trace gases, gases that make up less than 1% of the atmosphere, the Earth would freeze. And so by the early 1860s, the basic physics of what we now call the greenhouse effect was established. Fourier had identified the puzzle. Foote had shown that carbon dioxide traps heat. Tyndall had mapped out the mechanism in detail and identified the specific gases responsible. The Earth is warm because certain trace gases in the atmosphere absorb outgoing infrared radiation and send some of it back to the surface. Remove those gases, and the average temperature of the Earth drops from about 15 degrees Celsius to something like -18. That's a difference of 33 degrees. 33 degrees of warming, provided entirely by gases that make up a tiny fraction of the air you're breathing right now. But knowing that the greenhouse effect exists is one thing. The next question, the question that would take decades to answer and would eventually reshape civilization's understanding of its own future, was whether humans could change it. Whether burning coal and oil and gas could add enough carbon dioxide to the atmosphere to measurably warm the planet. And the first person to seriously tackle that question was a Swedish chemist with a pencil, a stack of data tables, and an almost unbelievable amount of patience. His name was Svante Arrhenius, and what he did with those data tables over the winter of 1894 and 1895 is one of the most remarkable feats of sheer computational stubbornness in the history of science. Arrhenius sat down and, by hand, calculated how changes in the concentration of carbon dioxide in the atmosphere would affect temperatures at different latitudes across the entire planet. He divided the Earth's surface into a grid, bands of latitude, slices of day and night, seasons, and for each cell in that grid, he worked out the energy balance. How much solar radiation comes in, how much infrared radiation goes out, how much gets absorbed by carbon dioxide and water vapor along the way. And he did all of this without a computer, without a calculator, really, in any modern sense, just logarithm tables, published measurements of lunar infrared radiation that had been gathered by the American astronomer Samuel Langley, and month after month of grinding arithmetic. Think about what that actually involves. For each latitude band, you have to estimate the incoming solar energy based on the angle of the sun, which changes with the seasons. Then, you have to figure out how much of the outgoing infrared gets caught by the atmosphere, which depends on how much carbon dioxide is present and how much water vapor is in the air at that latitude and that time of year. Water vapor is the tricky part, because the amount of water vapor the atmosphere can hold depends on temperature, which is the very thing you're trying to calculate. So there's a feedback loop built right into the problem. Arrhenius handled it with approximations, reasonable ones, but approximations nonetheless. And he just kept grinding through the numbers, cell by cell, season by season. He later described the work as tedious, which might be the understatement of the 19th century. What he found, when he finally assembled all those calculations into a coherent picture, was striking. If you doubled the amount of carbon dioxide in the atmosphere, took it from its then current level of roughly 295 parts per million to about 590, the average global temperature would rise by about 5 to 6 degrees Celsius. If you halved it, the temperature would drop by a similar amount, enough to plunge the world into ice age conditions. And here's what's remarkable about that number. Modern climate models, built on supercomputers running millions of lines of code and fed with satellite data Arrhenius couldn't have dreamed of, estimate that doubling carbon dioxide would raise temperatures by somewhere between 2.5 and 4.5 degrees Celsius, with a best estimate around 3. Arrhenius was high, but he was in the right ballpark, with a pencil and paper. In 1896. Now, Arrhenius wasn't worried about global warming. That's an important thing to understand about the context. He was actually trying to solve a completely different problem: the ice ages. By the 1890s, geologists had firmly established that the Earth had gone through multiple ice ages, periods when glaciers advanced far south of their current positions, covering much of Europe and North America in ice sheets kilometers thick. The evidence was everywhere: scratched bedrock, erratic boulders deposited far from their source, U-shaped valleys carved by rivers of ice. But nobody could explain what caused them. What could make the entire planet cool down enough to trigger an ice age and then warm back up again? Arrhenius thought carbon dioxide might be the answer. If volcanic activity slowed down for long periods, less carbon dioxide would be pumped into the atmosphere. Chemical weathering of rocks would continue to pull carbon dioxide out. The concentration would drop, the greenhouse effect would weaken, and the planet would cool. It was a plausible hypothesis, and his calculations showed the numbers could work. That was the point of the whole exercise, not to warn about fossil fuels, but to explain the ice ages. But he did think about fossil fuels. In a later paper and in a popular book he published in 1906, Arrhenius explicitly noted that humanity was burning coal at an increasing rate, and that this would add carbon dioxide to the atmosphere. He estimated that it might take about 3,000 years for industrial emissions to double atmospheric carbon dioxide. And, this is fascinating, he thought that would be a good thing. Arrhenius was Swedish. He lived through long, dark, freezing winters. The idea that the planet might warm up a few degrees sounded rather pleasant to him. He wrote about how future generations might enjoy more equable climates and more bountiful harvests. He saw it as a benefit, not a threat. He was wrong about the timeline, of course. Dramatically wrong. He underestimated how fast fossil fuel consumption would grow. But the core physics he laid out, that carbon dioxide warms the planet through infrared absorption, that the relationship between concentration and temperature is logarithmic, meaning each doubling produces roughly the same temperature increase, all of that has held up. Arrhenius gave the world the first quantitative estimate of climate sensitivity, and he did it with tools that belong in a museum. But here's the thing. Almost nobody paid attention. Or rather, people noticed the work, discussed it in scientific circles for a few years, and then mostly moved on. A Swedish physicist named Knut Ångström, the son of the famous spectroscopist Anders Ångström, published experiments in 1901 that seemed to show Arrhenius was wrong. Ångström's argument went something like this. Carbon dioxide already absorbs most of the infrared radiation in the wavelengths where it's active. Adding more carbon dioxide wouldn't make much difference because the absorption is already saturated, like adding more paint to a wall that's already fully coated. The color doesn't get any deeper. This saturation argument was influential, and for decades it gave scientists a reason to dismiss the whole idea that carbon dioxide could significantly affect climate. It seemed like a settled question. Carbon dioxide? Doesn't matter. The absorption bands are already full. And this is worth pausing on, because the saturation argument is one of the most important wrong turns in the history of climate science. It delayed serious investigation by decades. And it was wrong for a reason that's genuinely subtle. A reason that wouldn't be fully worked out until the 1950s. But we'll come back to that. For now, just notice what happened. By 1900, the basic physics of the greenhouse effect was understood. The key gases had been identified. A reasonable first estimate of climate sensitivity had been calculated, and then the whole line of inquiry went dormant. Not because it was disproven, but because one seemingly compelling objection, the saturation argument, made most scientists shrug and move on to other problems. The idea that human activities could change the climate was shelved, filed away as an interesting but probably irrelevant curiosity. The early 20th century saw climate science fragment into smaller, disconnected streams of research. Meteorologists were busy trying to forecast weather, which is a different problem from understanding long-term climate. Geologists continued studying ice ages, but focused more on astronomical theories. The idea that variations in Earth's orbit around the Sun might trigger glacial cycles. This line of thinking had been around since the 1840s, when a French mathematician named Joseph Hadamard first proposed it, and it was developed much more rigorously by a Scottish scientist named James Croll in the 1860s and 70s. Croll worked out that changes in the eccentricity of Earth's orbit, how elliptical versus how circular it is, could affect how much solar energy reaches different parts of the planet at different times of year. But the real champion of the orbital theory was a Serbian mathematician and engineer named Milutin Milanković, who spent decades, literally decades, starting around 1912, painstakingly calculating how 3 different orbital variations affect solar radiation at every latitude. The 3 cycles he focused on were eccentricity, which changes on a roughly 100,000-year cycle; obliquity, the tilt of Earth's axis, which varies between about 21.5 and 24.5 degrees on a roughly 41,000-year cycle; and precession, the wobble of the axis, which cycles every 26,000 years or so. Each of these changes how sunlight is distributed across the globe and across the seasons. Milanković argued that what matters most for triggering an ice age isn't how cold winters get, but how cool summers are. If summers in the high northern latitudes are cool enough that winter snow doesn't fully melt, it accumulates year after year, building into ice sheets. And the orbital cycles can make northern summers cooler without changing the total amount of solar energy the Earth receives. They just redistribute it. Milanković published his comprehensive calculations in 1941, right in the middle of World War II, which meant hardly anyone read them at first. His work would eventually be confirmed decades later by deep-sea sediment cores, but during his lifetime, it remained controversial. And the important thing for our story is that the orbital theory, while correct in explaining the timing of ice ages, doesn't explain everything. The orbital changes alone don't produce enough of a temperature shift to account for the full swing between glacial and interglacial periods. Something amplifies them. And that something, as it turns out, is carbon dioxide. But that connection wouldn't be clearly established for another 40 years. So there's this strange period, roughly 1900 to 1950, where climate science is sort of scattered. People are working on pieces of the puzzle in isolation. Weather forecasting is becoming its own discipline. Oceanographers are starting to understand ocean circulation, but don't yet connect it to climate in a systematic way. And the carbon dioxide question is just sitting there, gathering dust, because of that saturation argument. The person who blew the saturation argument apart was a Canadian-born physicist named Gilbert Plass, working in the United States in the 1950s. And what Plass understood, that Ångström and his contemporaries had missed, was something about how the atmosphere actually works in 3 dimensions. See, Ångström's experiment had looked at carbon dioxide absorption in a short tube of gas at sea level pressure. And yes, in that tube, adding more carbon dioxide didn't seem to absorb much more infrared. The absorption bands looked saturated. But the atmosphere isn't a tube. It's a column of air stretching from the surface up to the edge of space, and as you go higher, the air gets thinner and colder. The infrared radiation that escapes to space doesn't leave from the surface. It leaves from high up in the atmosphere, from an altitude where the air is thin enough that carbon dioxide molecules are sparse enough to let some radiation slip through. And here's the key insight. If you add more carbon dioxide to the atmosphere, that effective emission altitude, the height from which radiation finally escapes to space, moves upward, higher in the atmosphere, and higher means colder. And a colder emitting layer radiates less energy to space, which means the planet has to warm up until a new balance is reached. The absorption bands at the surface might be saturated, but at the top of the atmosphere, where it actually matters for the planet's energy balance, adding more carbon dioxide always makes a difference. Plass published a series of papers in the mid-1950s laying this out, and he explicitly warned that fossil fuel burning was increasing atmospheric carbon dioxide and would warm the planet. He estimated about 1 degree Celsius of warming per century at the rate things were going. And unlike Arrhenius, he didn't think this was good news. But Plass was working with limited data, and his calculations, while pointing in the right direction, had some significant uncertainties. What he really needed, what the whole field desperately needed, was actual measurements. Not calculations, not estimates, not theoretical arguments. Someone needed to go out and measure how much carbon dioxide was actually in the atmosphere and whether it was increasing. And that someone was already getting ready to do exactly that, on a volcano in the middle of the Pacific Ocean, with an instrument so precise it could detect changes in carbon dioxide concentration as small as a fraction of a part per million. His name was Charles David Keeling, and he was, by all accounts, a man almost obsessively devoted to precision. Keeling was a postdoctoral researcher at Caltech in the early 1950s, and he'd been given what seemed like a fairly straightforward task: measure the concentration of carbon dioxide in the air around Big Sur, California, and in the waters of the Pacific. Simple enough, right? Except that when Keeling started taking measurements, he found that the existing methods were, to put it politely, a mess. Different researchers using different techniques were getting wildly different numbers. Some measurements suggested carbon dioxide levels of 300 parts per million. Others said 350. Some said even higher. The data was all over the place, and nobody could agree on a baseline. And Keeling, who had this almost compulsive need for accuracy, found this deeply unsatisfying. So he did what a certain kind of scientist does. He built a better instrument. He refined a technique using a manometric gas analyzer that could measure carbon dioxide with extraordinary precision, and then he started sampling air obsessively. Morning, afternoon, evening, night. Different locations, different altitudes, different weather conditions. And here's what he noticed, and this is one of those quiet discoveries that seems small, but turns out to be enormous. He found that if you measured air in a clean, well-mixed environment, away from cities, away from forests, away from anything that was either producing or absorbing carbon dioxide locally, you got a remarkably consistent number, about 310 parts per million, every time. The background concentration of carbon dioxide in the atmosphere was not some noisy, variable mess. It was a single, stable, global number. And that meant you could track it. If you had a precise enough instrument in a clean enough location, you could watch that number and see if it changed over time. This was the insight that changed everything. Not a theoretical argument, not a calculation, not a model. Just the realization that the atmosphere was well mixed enough that a single monitoring station, placed carefully, could serve as a thermometer for the entire planet's carbon dioxide level. And Keeling knew exactly where to put it. Mauna Loa, on the Big Island of Hawaii. Think about why that's such a brilliant choice. It's in the middle of the Pacific Ocean, thousands of miles from any major industrial source. It's at an altitude of about 11,000 feet, well above the local inversion layer that traps surface-level pollution. The air that reaches the summit has been churned and mixed across the entire hemisphere. It's about as close to a sample of the whole atmosphere as you can get without putting an instrument on a satellite. And in 1958, with funding from the International Geophysical Year, this massive global scientific collaboration, Keeling set up his instruments on Mauna Loa and started recording. The first full year of data was 1959, and almost immediately Keeling saw something remarkable. The carbon dioxide concentration wasn't just a flat line at 315 parts per million. It oscillated. It went up in the winter and down in the summer. Every year, like clockwork. And if you think about it, the reason is beautiful. During the Northern Hemisphere's growing season, spring and summer, all those billions of trees and plants across North America, Europe, and Asia are photosynthesizing, pulling carbon dioxide out of the air, converting it into leaves and wood and roots. The planet literally breathes in. And then, in autumn and winter, when the leaves fall and decay, when the biological activity slows down, carbon dioxide gets released back into the atmosphere. The planet breathes out. Keeling was watching the Earth breathe. From a single instrument on a volcano in Hawaii, he could see the seasonal pulse of every forest in the Northern Hemisphere. But here's the thing that mattered even more than the seasonal cycle. When Keeling looked at the average from year to year, stripping away that beautiful oscillation, the baseline was going up. Every year, the average was a little higher than the year before. Not by a lot, about 1 part per million per year in those early days, but it was unmistakable. Steady, relentless, upward. Carbon dioxide was accumulating in the atmosphere, and it was doing so at a rate that matched what you'd expect from fossil fuel combustion. The theoretical predictions that Arrhenius had made in 1896, that Callendar had refined in the 1930s, that Plass had warned about in the 1950s, they were all confirmed by this single, elegant measurement. The Keeling curve, as it came to be known, is one of the most important data sets in all of science. It's still being measured today from the same observatory, using the same basic approach, and that line has never stopped going up, not once, not for a single year. Now, Keeling almost lost his funding multiple times. This is one of those frustrating stories about how science actually works in practice. The measurements were expensive to maintain, and they didn't produce the kind of flashy results that funding agencies love. It's just a number, going up a little bit every year. Some administrators at the Scripps Institution of Oceanography, where Keeling was based, questioned whether it was worth the cost. At various points in the 1960s and 70s, his budget was cut, his staff was reduced, and there were gaps in the record that he had to fight to fill. Keeling himself was apparently not the easiest person to work with. He was demanding, meticulous to the point of being difficult, and he didn't suffer fools gladly. But he was right, and he knew he was right, and he kept that instrument running through sheer stubbornness. If he had lost that funding permanently, if there had been a 5-year gap in the record, the entire history of climate science would look different. Sometimes the most important thing a scientist does is just keep measuring. So by the mid-1960s, the scientific community had several crucial pieces in place. They understood the greenhouse effect. Fourier, Foote, Tyndall had established that. They understood which gases mattered and why. Carbon dioxide, water vapor, methane. They had Place's resolution of the saturation argument, showing that adding carbon dioxide always matters at the effective emission altitude. And now they had Keeling's data showing that carbon dioxide was, in fact, increasing in the atmosphere. The next question was obvious. What would that actually do to the climate? Not in theory, not in a back-of-the-envelope calculation like Arrhenius had done, but in a rigorous, physically grounded way that accounted for the full complexity of the atmosphere. The clouds, the water vapor, the ocean circulation, the ice, the winds, all of it interacting simultaneously. And this is where we need to talk about the birth of climate modeling, which is really the birth of using computers to simulate the atmosphere. Because the atmosphere is, to put it mildly, complicated. You can't solve it with pencil and paper. Arrhenius tried, and it took him a full year of hand calculations to get an approximate answer. The real atmosphere has fluid dynamics, radiation, convection, phase changes of water, turbulence at every scale. It's one of the most complex physical systems we know of. And the only way to get a handle on it is to divide the atmosphere into a grid, write down the equations of physics for each grid cell, and let a computer march them forward in time, step by step. The person who really pioneered this approach for climate, as opposed to weather forecasting, which is a related but different problem, was Shukuro Manabe. He was a Japanese physicist who came to the United States in 1958, the same year Keeling started his measurements on Mauna Loa, and he ended up at the Geophysical Fluid Dynamics Laboratory, which was then part of the U.S. Weather Bureau. Manabe was quiet, methodical, and brilliant, and he had a gift for knowing which complexities to include in a model and which to leave out. Because here's the thing about modeling. If you try to include everything, you get a model so complex that you can't understand what it's telling you, and it takes forever to run even on the fastest computers. The art is in simplification, keeping the essential physics, stripping away the noise. In 1967, Manabe and his colleague Richard Wetherald published a paper that is one of the landmarks of climate science. They built a one-dimensional model of the atmosphere, just a single column of air, stretching from the surface to the top of the atmosphere, divided into layers. No horizontal variation, no continents, no oceans, no seasons. Just a column. But within that column, they included the real physics of radiation, how sunlight comes in, how infrared radiation goes out, how each layer of the atmosphere absorbs and emits based on its temperature and its concentration of greenhouse gases. And critically, they included convection, the fact that when the lower atmosphere gets too warm relative to the upper atmosphere, air rises and mixes, carrying heat upward. This is something Arrhenius had completely ignored, and it matters enormously. They ran their model with the current concentration of carbon dioxide, and it produced a surface temperature that matched reality pretty well. Then they doubled the carbon dioxide in the model and let it reach a new equilibrium. And the answer they got was a warming of about 2.3 degrees Celsius. That number, the warming you get from doubling carbon dioxide, is called climate sensitivity, and it's the single most important number in all of climate science. Arrhenius had estimated 5 to 6 degrees back in 1896, though his calculation had some errors that happened to partially cancel out. Manabe and Weatherald's 2.3 degrees was lower, but it was based on much more rigorous physics. And here's a detail that's worth pausing on. Their model also showed that when you warm the atmosphere, you get more water vapor, because warmer air holds more moisture, and water vapor is itself a greenhouse gas. So the water vapor amplifies the initial warming from carbon dioxide. This water vapor feedback roughly doubles the warming you'd get from carbon dioxide alone. Manabe and Weatherald quantified this for the first time, and it's still one of the most important feedbacks in the climate system. But a single column of air isn't the real atmosphere. The real atmosphere has winds, it has oceans, it has ice caps that reflect sunlight and can grow or shrink. It has clouds, and clouds are, honestly, the single hardest thing to get right in a climate model, because they both reflect incoming sunlight, which cools the planet, and trap outgoing infrared radiation, which warms it, and the net effect depends on the type of cloud, its altitude, its thickness, its droplet size. Clouds are the reason that climate sensitivity still has an uncertainty range today, more than 50 years after Manabe's first calculation. But Manabe wasn't done with one-dimensional models. By 1969, he and his colleague Kirk Bryan had built something far more ambitious, a three-dimensional model that coupled the atmosphere to the ocean. This was the first general circulation model that tried to simulate the full three-dimensional climate system, with air and water moving in all directions, exchanging heat and moisture. It was crude by modern standards. The grid cells were enormous, hundreds of kilometers across. But it captured the essential dynamics. The tropics were warm, the poles were cold, the trade winds blew in the right direction, and the ocean currents looked roughly like the real ones. And when they added carbon dioxide to this model, they got results that were broadly consistent with the simpler one-dimensional calculation, but with much more spatial detail. The poles warmed more than the tropics. The land warmed more than the ocean. These patterns, which Manabe predicted in the late 1960s, are exactly what we observe today. Meanwhile, while Manabe was building his models in Princeton, something else was happening that would prove just as important for understanding past climates. Researchers were learning to read the history of Earth's atmosphere, locked away in the most unlikely of archives, ancient ice. Deep in the ice sheets of Greenland and Antarctica, snow falls year after year, compressing into layers of ice that preserve tiny bubbles of air, trapped at the moment the snow turned to ice. Those bubbles are samples of the ancient atmosphere. You can extract them, analyze them, and find out exactly how much carbon dioxide and methane were in the air, hundreds, thousands, even hundreds of thousands of years ago. And the story those ice cores began to tell in the 1960s and 70s was one of the most dramatic confirmations in all of climate science. Because what those tiny bubbles revealed was a lockstep dance between carbon dioxide and temperature stretching back further than anyone had imagined. Now, the idea of drilling into ice to learn about the past wasn't entirely new. Glaciologists had been studying ice layers for decades, counting annual bands the way you'd count tree rings, measuring the thickness of each year's snowfall, looking at dust and volcanic ash trapped in the layers. But the real breakthrough came when scientists figured out that those air bubbles, those little pockets of ancient atmosphere sealed inside the ice, could be carefully extracted and measured for their gas composition. And not just the gases. The ice itself, the water molecules, carried a chemical signature of the temperature at the time the snow originally fell. This is where it gets a little bit into chemistry, but it's worth understanding because it's genuinely elegant. Water molecules are made of hydrogen and oxygen, right? But not all oxygen atoms are the same. Most oxygen in nature is oxygen-16. That's the light, common isotope, with 8 protons and 8 neutrons. But a small fraction is oxygen-18, which has 2 extra neutrons and is slightly heavier. When water evaporates from the ocean, the lighter molecules, the ones with oxygen-16, evaporate a little more easily. They're lighter. They escape the surface more readily. So water vapor in the atmosphere is slightly enriched in the lighter isotope compared to the ocean. Now, as that moisture-laden air moves toward the poles and cools, it starts to precipitate. Rain, then snow. And here's the key. When water condenses, the heavier molecules condense out preferentially. They're heavier, they drop out first. So as air masses travel poleward, getting colder and losing moisture along the way, the remaining vapor becomes progressively more depleted in oxygen-18. By the time that moisture falls as snow over Greenland or Antarctica, it's strongly depleted in the heavy isotope. And the colder the climate, the more depleted it gets, because the air has cooled more, wrung out more of the heavy molecules along the way. So the ratio of oxygen-18 to oxygen-16 in an ice layer is a thermometer, a natural built-in thermometer that tells you how cold it was when that snow fell. The more depleted in oxygen-18, the colder the climate. And this works beautifully, layer by layer, going back in time as you drill deeper into the ice sheet. The early ice core work happened in Greenland. In the 1960s, a team at Camp Century, a U.S. military base built inside the Greenland ice sheet, which is a whole story in itself, a nuclear-powered base under the ice during the Cold War, drilled a core that reached bedrock at about 1,400 meters deep. The Danish physicist Willy Dansgaard analyzed the oxygen isotope ratios in that core and showed clear oscillations in temperature going back over 100,000 years. You could see the last ice age. You could see the warm period before it. The ice was a climate archive of extraordinary resolution. But the really transformative cores came from Antarctica, where the ice is even thicker and the record stretches back further. The Soviet Antarctic station at Vostok, one of the most inhospitable places on Earth, temperatures there have dropped below -89 degrees Celsius. The coldest ever recorded on the planet's surface, became the site of one of the most important scientific drilling projects in history. Starting in the 1970s and continuing through the 80s and 90s, Soviet and then Russian and French teams drilled deeper and deeper into the East Antarctic ice sheet. By 1998, the Vostok core had reached over 3,300 meters deep and contained ice going back about 420,000 years. And here's what they found when they analyzed both the temperature record from the oxygen isotopes and the carbon dioxide from the trapped air bubbles. The two curves matched, not roughly, not approximately. They tracked each other with astonishing fidelity through 4 complete glacial cycles. When temperature dropped during an ice age, CO2 dropped too, falling to around 180 parts per million. When temperature rose during a warm interglacial period, CO2 rose with it, up to about 280 parts per million, back and forth, 4 times, over 400,000 years. The correlation was undeniable. Now this is where people sometimes get confused, and it's worth pausing on because it matters. The ice cores showed that in the natural glacial cycles, temperature changes often led CO2 changes by several hundred years. The warming started first, and then CO2 rose. And some people have pointed to this and said, well, that proves CO2 doesn't cause warming. It's the other way around. Temperature causes CO2 changes. But here's the thing. That's not actually a contradiction. Think about what's happening. The glacial cycles are initiated by those Milankovitch orbital variations we talked about earlier. The slow wobbles and tilts and stretches of Earth's orbit. Those orbital changes alter how much sunlight hits different parts of the planet at different times of year. And the initial warming, triggered by orbital geometry, does something important. It warms the oceans. And warm oceans release carbon dioxide, just like a warm soda goes flat faster than a cold one. So the initial orbital nudge causes a little warming, which causes the oceans to release CO2, which causes more warming through the greenhouse effect, which releases more CO2, and so on. It's a feedback loop. The CO2 amplifies the orbital signal. Without that amplification, the tiny changes in solar energy distribution from orbital variations wouldn't be nearly enough to swing the planet in and out of ice ages. The orbital forcing alone changes global average temperature by maybe a degree or so. The full glacial-interglacial swing is more like 5 to 6 degrees globally, and even more at the poles. The difference, that extra warming, comes largely from CO2 and other feedbacks like ice albedo. So the ice cores didn't undermine the greenhouse theory. They confirmed it powerfully. They showed that CO2 and temperature are intimately coupled in the Earth system, and that CO2 acts as a critical amplifier. And they gave scientists something else incredibly valuable, a calibration point. If you know how much CO2 changed and how much temperature changed over these natural cycles, you can estimate climate sensitivity, how much warming you get per unit of CO2 increase. And the numbers that came out of the ice core analysis were broadly consistent with what Manabe had calculated from his models, somewhere around 2 to 4 degrees Celsius for a doubling of CO2. The models and the geological record were telling the same story. The Vostok core was later surpassed by the European project for ice coring in Antarctica, the EPICA project, which drilled at a site called Dome C and recovered ice going back about 800,000 years, covering 8 full glacial cycles. Same pattern. Every single time. CO2 and temperature, rising and falling together, with CO2 never once exceeding about 300 parts per million during any of those 800,000 years. And then you look at the present day, and CO2 is above 420 parts per million and climbing. That number has no precedent in 800 millennia of Earth's history. Think about that for a second. 800,000 years of natural variation, and the atmosphere never had this much carbon dioxide. Not once. But let's come back to the 1970s for a moment, because something important was happening in the broader scientific and political landscape that shaped how climate science developed from that point forward. You might have heard the claim that in the 70s, scientists were predicting global cooling, an imminent ice age. And there's a grain of truth to it, but only a grain. And the full story is more interesting than the myth. What actually happened was this. By the early 70s, scientists understood two competing influences on climate. On one hand, CO2 was increasing and should cause warming. On the other hand, aerosol pollution, tiny particles of sulfate and soot from burning fossil fuels and other industrial activity, was also increasing, and aerosols reflect sunlight, which should cause cooling. The question was, which effect would dominate? A few papers, notably one by Rasool and Schneider in 1971, suggested that if aerosol emissions kept growing rapidly, the cooling effect might win out. Newsweek ran a famous article in 1975 about the cooling hypothesis. It made a splash. But here's what the historical record actually shows. A survey of the scientific literature from 1965 to 1979 found that even during the supposed global cooling scare, the majority of peer-reviewed papers that took a position on future climate predicted warming, not cooling. The ratio was roughly 6-1 in favor of warming. The cooling hypothesis was a minority view even at the time. It got outsized media attention, but it was never the scientific consensus. And what resolved the question was partly the Clean Air Acts in the United States and similar legislation in Europe, which dramatically reduced aerosol emissions starting in the 70s. Sulfate pollution dropped, the skies cleared, and the cooling influence weakened, while CO2 kept rising. By the early 1980s, the warming signal was becoming unmistakable in the temperature record. And that brings us to one of the most consequential moments in the public history of climate science, the summer of 1988. It was brutally hot across the United States. Drought had parched the Midwest. The Mississippi River was running so low that barge traffic was disrupted. Yellowstone National Park was on fire. And on June 23rd, a NASA climate scientist named James Hansen sat down before a U.S. Senate committee and said something that no scientist of his stature had said so plainly in a public forum before. He said the greenhouse effect had been detected, and it was changing our climate now. Not in the future. Now. He said he was 99% confident that the warming trend was not natural variation. He brought charts. He brought data, and he spoke in clear, declarative sentences that left no room for ambiguity. Hansen had been working on climate models at NASA's Goddard Institute for Space Studies since the 1970s. His models, like Manabe's, predicted warming from CO2 increases. But Hansen went further than most scientists were comfortable going at the time. He was willing to say publicly that the warming was already happening, and that it was caused by human activity. His testimony made front-page news. The New York Times ran it above the fold, and it changed the conversation. Before Hansen's testimony, climate change was largely a scientific concern, discussed in journals and at conferences. After it, climate change became a political issue, a public issue, something that senators and presidents and prime ministers had to have positions on. But Hansen's boldness also made him controversial within the scientific community. Some colleagues thought he was getting ahead of the data, that the signal hadn't yet clearly emerged from the noise of natural variability. Others thought he was exactly right, and that scientists had been too cautious for too long. This tension between scientific caution and the urgency of communicating risk would define climate science for the next 3 decades and beyond. And in that same year, 1988, something else happened that would shape the trajectory of climate science in ways both productive and complicated. The United Nations established the Intergovernmental Panel on Climate Change, the IPCC. Its mandate was to assess the scientific literature on climate change and provide policymakers with clear, authoritative summaries of what was known, what was uncertain, and what the risks were. The IPCC didn't do new research itself. Instead, it assembled hundreds, eventually thousands, of scientists from around the world to review and synthesize the existing research. Its first assessment report came out in 1990, and it concluded that human activities were substantially increasing atmospheric greenhouse gases, that this would enhance the greenhouse effect and result in additional warming, and that the global average temperature would likely rise by about 1 to 3 degrees Celsius by the end of the 21st century if emissions continued unchecked. Now, that range might sound modest, but think about what it represented. This was the first time an international body of scientists had collectively looked at all the evidence: the physics, the models, the ice cores, the temperature records, and said in one voice, "Yes, this is real, this is happening, and here's roughly how bad it could get." And the language was careful, deliberately careful. Because the IPCC process is built on consensus, and consensus among hundreds of scientists from dozens of countries means every sentence gets scrutinized, debated, sometimes fought over word by word. The result is language that tends toward the conservative, the hedged, the cautious, which is both the IPCC's greatest strength and, some would argue, its most significant limitation. But let's stay with that first report for a moment, because the early 90s were a fascinating period in climate science. The report landed just as the world was going through enormous geopolitical change. The Berlin Wall had just fallen, the Soviet Union was dissolving, and there was this brief window of extraordinary international optimism. People genuinely believed that global cooperation on big problems was possible in ways it hadn't been before. And so in 1992, world leaders gathered in Rio de Janeiro for the Earth Summit, formerly called the United Nations Conference on Environment and Development, and they signed the United Nations Framework Convention on Climate Change, the UNFCCC. This was the treaty that established the basic architecture for international climate negotiations. Its stated objective was to stabilize greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. That phrase, dangerous anthropogenic interference, would become one of the most debated strings of words in environmental policy. What counts as dangerous? Dangerous for whom? Over what timescale? The science could inform those questions, but it couldn't answer them alone. They were fundamentally questions about values, about risk tolerance, about whose suffering counts and how much. Meanwhile, the science kept advancing, and one of the most important developments of the early 90s happened not in a laboratory or on a mountaintop, but inside computers. Climate models were getting substantially more sophisticated. Remember how Manabe and Weatherald had built that pioneering model back in '67? A single column of atmosphere, radiative convective equilibrium, water vapor feedback? And then Manabe and Bryan had coupled the atmosphere to an ocean in '69? Well, by the early 90s, these models had evolved into what scientists call general circulation models, or GCMs, and they were becoming genuinely three-dimensional representations of the entire Earth system. Multiple atmospheric layers, ocean circulation patterns, sea ice dynamics, land surface processes. Each model divided the Earth's surface into a grid. Imagine a mesh draped over the globe, and then calculated the physics at every grid point, at every time step, marching forward through simulated decades and centuries. And here's what made these models so powerful and so important for the detection question: the question of whether human influence on climate could actually be identified in the observational record. You could run these models in different configurations. You could run them with only natural forcings, volcanic eruptions, solar variability, and see what kind of temperature patterns they produced. Then you could run them with only human forcings, greenhouse gases, aerosols, and see a different pattern. And then you could run them with everything combined and compare the result to what the real world actually showed. This technique became known as detection and attribution, and it was pioneered in the early 90s by a number of groups, but one name that stands out is Ben Santer. Santer was a climate scientist at Lawrence Livermore National Laboratory, and his work in the mid-90s became both a scientific milestone and a cautionary tale about what happens when science collides with politics. Here's what Santer and his colleagues did. Instead of just looking at whether the globe was warming overall, which could, theoretically, have natural explanations, they looked at the pattern of warming, the fingerprint. Think of it this way. If the sun were getting brighter, you'd expect warming pretty much everywhere, at all altitudes. But if greenhouse gases were trapping more heat in the lower atmosphere, you'd expect a specific pattern: warming in the troposphere, cooling in the stratosphere, more warming at night than during the day, more warming in winter than in summer at high latitudes, more warming over land than over ocean. Each forcing mechanism leaves its own distinctive signature, its own fingerprint, on the climate system. And what Santer found was that the observed pattern of warming matched the greenhouse gas fingerprint far better than it matched any natural forcing pattern. This was a huge deal. It moved the science from saying, "We expect warming," to saying, "We can see the specific pattern of warming that greenhouse gases would cause, and it's there in the data." His work contributed directly to the most famous sentence in the IPCC's Second Assessment Report, published in 1995. That sentence read, "The balance of evidence suggests a discernible human influence on global climate." Discernible human influence. 5 words that changed everything. Again, notice the careful language. The balance of evidence suggests, not proves, not demonstrates beyond doubt. Suggests. And yet even that cautious phrasing provoked a firestorm. What happened to Santer after that report is worth knowing, because it reveals the forces that were gathering against climate science in the 90s. Fossil fuel interests and their allies launched a campaign to discredit both the science and the scientist. Santer was accused of improperly altering the chapter he'd led, Chapter 8 of the Working Group 1 report, to make the conclusion sound more definitive than the evidence warranted. The accusations were published in the Wall Street Journal. They were amplified by industry-funded organizations, and they were, by the assessment of the scientific community and subsequent investigations, unfounded. The changes Santer had made were part of the normal IPCC review process, responding to reviewer comments, as every lead author is expected to do. But the damage to his reputation, at least in public perception, was real. He received hate mail. He received death threats. And he spent years defending work that the scientific community broadly supported. This is the part of the climate science story that's hard to tell without getting into politics, but it's essential, because from the mid-90s onward, the history of climate science cannot be separated from the history of organized efforts to cast doubt on it. And the playbook was borrowed, sometimes literally, sometimes by the same people, from the tobacco industry's decades-long campaign to obscure the link between smoking and cancer. The strategy wasn't to prove that climate change wasn't happening. It was simply to manufacture uncertainty, to make the public think the science was more contested than it actually was. Doubt is our product, as one infamous tobacco industry memo had put it. And doubt, it turned out, was remarkably effective at delaying action. But let's come back to the science itself, because through all of this, the research kept accumulating, and the models kept improving, and the observations kept piling up. One of the most important observational developments of the 90s was the launch of dedicated satellite missions for monitoring Earth's climate. Satellites had been observing the planet since the 60s, of course, but the 90s and early 2000s brought a new generation of instruments specifically designed for climate-relevant measurements: sea level, ice sheet mass, ocean heat content, atmospheric temperature profiles, cloud properties, radiation budgets. All of these could now be monitored globally, continuously, from space. And what the satellites showed was consistent with what the models predicted and what the ground-based observations indicated. The planet was warming. The ice was melting. Sea level was rising. Let's talk about sea level for a moment, because it's one of those things that sounds abstract until you think about what it actually means. Sea level rises for two main reasons. The first is thermal expansion. As ocean water warms, it expands, taking up more volume. This is just basic physics, the same reason a mercury thermometer works. The second is the addition of new water from melting land ice, glaciers, ice caps, and the big ice sheets on Greenland and Antarctica. Now, the ocean is enormous. It covers about 70% of the Earth's surface. So even a small amount of thermal expansion, spread across all that area, translates into a measurable rise. And the numbers, while they sound small in isolation, are staggering in their implications. Over the 20th century, global mean sea level rose by roughly 15 to 20 centimeters, about 6 to 8 inches. That might not sound like much, but think about what it means for a low-lying coastal city during a storm surge. Think about what it means for a Pacific island nation where the highest point is 3 meters above sea level. Every centimeter matters. Every centimeter changes the calculus of flooding, of saltwater intrusion into freshwater aquifers, of coastal erosion, and the rate of rise was accelerating. The rate in the last few decades of the 20th century was roughly double the rate of the first few decades. By the time the IPCC released its third assessment report in 2001, the language had sharpened. The key finding now stated that most of the observed warming over the last 50 years was likely due to the increase in greenhouse gas concentrations. Likely, in IPCC terminology, means greater than 66% probability, and the report projected future warming of 1.4 to 5.8 degrees Celsius by 2100, a wider range than the first report, partly because the models now included a broader range of emission scenarios, different possible futures depending on how much fossil fuel the world would burn. And then came the fourth assessment report in 2007, and the language tightened again. Now it was very likely, greater than 90% probability, that most of the observed increase in global average temperatures since the mid-20th century was due to the observed increase in anthropogenic greenhouse gas concentrations, 90%. And the report was awarded the Nobel Peace Prize, shared with Al Gore, which was both a recognition of the science and a deeply polarizing moment. Some scientists were uncomfortable with the prize, feeling it further politicized what should be a purely scientific endeavor. Others saw it as long overdue recognition of the urgency of the problem. But here's what I find most striking about the progression of those IPCC reports. Watch the confidence levels climb. 1995, the balance of evidence suggests. 2001, likely. 2007, very likely. 2013, the fifth assessment report. Extremely likely, greater than 95% probability. Each report reflected not just more data, but better models, more sophisticated detection and attribution studies, longer temperature records, more ice core data, more satellite observations, more understanding of feedbacks and forcings. The science was converging, tightening, narrowing the uncertainties. And yet public perception, at least in some countries, was moving in the opposite direction, with doubt and skepticism actually increasing in certain demographics during the 2000s. That gap between scientific confidence and public confidence is one of the most remarkable features of the climate story, and it has everything to do with the organized disinformation campaigns we touched on a moment ago, combined with the deeply human difficulty of grappling with a slow-moving, invisible, globally distributed threat. But while the IPCC was synthesizing the science, other researchers were pushing into territory that would prove just as consequential: the study of climate tipping points. And this is where the story gets genuinely unsettling, because tipping points introduce the possibility that climate change isn't just a gradual, linear process where you add a little more CO2 and get a little more warming in a nice, predictable way. Instead, there might be thresholds in the Earth system, critical points beyond which a change becomes self-reinforcing, where the system doesn't just shift a little, it flips into an entirely different state, and getting it back is either incredibly difficult or, on any human timescale, essentially impossible. Think of it like pushing a ball up a hill. For a while, you push, and the ball stays on your side, maybe rolling back a little when you let go. But once it crests the top, it rolls down the other side under its own momentum, and no amount of pushing from where you're standing is going to bring it back. That's the essential idea of a tipping point. You cross a threshold and the system takes over, driving itself toward a new equilibrium that might be radically different from the one you started with. Now, the concept itself isn't new. Scientists had been thinking about abrupt climate change for decades. Remember those ice cores from Vostok and Epica Dome Sea? They showed the broad, slow oscillations of glacial and interglacial cycles. But when researchers looked more closely at the Greenland ice cores, particularly the cores drilled at sites called GRIP and GISP2 in the early 1990s, they found something that made their stomachs drop. Buried in the ice were records of temperature changes that happened not over millennia, not over centuries, but over decades, sometimes even less. These events, which came to be known as Dansgaard-Oeschger events after the Danish and Swiss scientists who first described them, showed temperature swings of 8 to 15 degrees Celsius in Greenland, happening in as little as a few decades. That's an almost incomprehensible rate of change. And they happened repeatedly during the last ice age, these sudden, dramatic warmings followed by slower coolings, over and over again. The mechanism behind them is still debated in detail, but the leading explanation involves the Atlantic meridional overturning circulation, that vast conveyor belt of ocean currents that carries warm water northward near the surface and cold, dense water southward in the deep ocean. You've probably heard of the Gulf Stream, which is part of this system. It's one of the reasons Western Europe has a relatively mild climate for its latitude. London is at the same latitude as Calgary, but London doesn't get Calgary winters, and a big part of that is because the ocean is delivering enormous amounts of heat to the North Atlantic. The overturning circulation is driven by density differences. When warm, salty water reaches the far North Atlantic, it cools, becomes denser, and sinks. That sinking is what pulls the whole conveyor along. But here's the thing. If you dump a lot of fresh water into the North Atlantic, say from melting ice sheets, you reduce the salinity, which reduces the density, which means the water doesn't sink as readily. Slow down the sinking, and you slow down the whole circulation. Slow it down enough, and it might shut off entirely. And if it shuts off, Europe loses that ocean heat delivery system. The tropics and southern hemisphere warm because the heat isn't being exported northward anymore. Rainfall patterns shift across entire continents. Monsoons weaken or migrate. The whole climate reorganizes around a new pattern. This isn't speculation. There's strong evidence that exactly this kind of shutdown happened during an event called the Younger Dryas, about 12,800 years ago, when temperatures in the North Atlantic region plunged back to near glacial conditions for over 1,000 years, right in the middle of the warming trend coming out of the last ice age. The leading hypothesis is that a massive pulse of meltwater, possibly from a collapsing ice dam over a huge glacial lake in North America, flooded into the Atlantic and shut down the overturning circulation like flipping a switch. So when scientists started thinking seriously about modern tipping points, the Atlantic circulation was near the top of the list. And the concern isn't hypothetical. Observations since the mid-2000s have suggested that the overturning circulation has already weakened, perhaps by 15% or so compared to the mid-20th century, though the measurements are tricky and the record is short. A monitoring array called RAPID, deployed across the Atlantic at about 26 degrees north latitude starting in 2004, has been tracking the circulation strength, and it's shown significant variability and a possible declining trend. Whether this represents the early stages of a tipping point approach or just natural fluctuation is one of the most important open questions in climate science right now. But the Atlantic circulation is just one of several potential tipping elements. Let's talk about ice sheets, because this is where the stakes become almost hard to comprehend. The Greenland ice sheet contains enough frozen water to raise global sea level by about 7 meters. That's roughly 23 feet. The West Antarctic ice sheet holds enough for another 3 to 5 meters. And both of these ice sheets have internal dynamics that could make their collapse self-sustaining once it begins. For Greenland, the key feedback is elevation. As the ice sheet melts and thins, its surface drops to lower altitudes where the air is warmer. Warmer air means more melting, which means the surface drops further, which means even warmer temperatures, and so on. At some point, the ice sheet passes a threshold where it can no longer sustain itself, even if you stopped adding CO2 to the atmosphere tomorrow. It just keeps melting because it's too low and too warm. Some modeling studies have suggested that threshold might be crossed somewhere between 1 and 3 degrees Celsius of global warming above pre-industrial levels. We've already passed 1.2 degrees. Think about what that means for a moment. For West Antarctica, the mechanism is different and in some ways even more alarming. Much of the West Antarctic ice sheet sits on bedrock that's below sea level, and the bedrock slopes downward as you move inland from the coast. This creates a situation called marine ice sheet instability. As warm ocean water eats away at the edges of the ice where it meets the sea, the grounding line, where the ice lifts off the bedrock and starts floating, the grounding line retreats inland. But because the bedrock slopes downward inland, the retreating grounding line encounters ice that's thicker and thicker, which means the ice front gets taller, which means more ice is exposed to warm water, which means faster melting, which means faster retreat. It's a positive feedback loop. Once it starts, it accelerates. In 2014, 2 separate research teams published papers suggesting that the collapse of several glaciers in the Amundsen Sea sector of West Antarctica might have already begun, and that the process was likely irreversible. Eric Rignot of NASA's Jet Propulsion Laboratory described it as a point of no return. The glaciers in question, Pine Island, Thwaites, and several others, are sometimes called the weak underbelly of West Antarctica. Thwaites alone, a glacier roughly the size of Florida, has been called the Doomsday Glacier in popular press, which scientists generally find unhelpful as a label, but not entirely inaccurate in terms of the consequences. If Thwaites collapses entirely, it could contribute around 65 centimeters of sea level rise on its own, and its collapse could destabilize neighboring glaciers, potentially unlocking meters of additional rise over centuries. And there are other tipping elements beyond ice and ocean currents. The Amazon rainforest, which generates a significant portion of its own rainfall through transpiration. Trees pulling water from the soil and releasing it into the atmosphere, where it forms clouds and falls as rain further west, could reach a point where deforestation and drought reduce that moisture recycling enough that the forest can no longer sustain itself, and large portions convert to savanna. The permafrost across Siberia, Alaska, and northern Canada contains roughly twice as much carbon as the entire atmosphere does right now, locked in frozen organic matter. As the Arctic warms, and it's warming 2 to 4 times faster than the global average, a phenomenon called Arctic amplification that Manabe's early models actually predicted, that permafrost thaws and microbes begin decomposing the organic matter, releasing CO2 and methane. Methane is a particularly potent greenhouse gas, roughly 80 times more effective at trapping heat than CO2 over a 20-year period. So thawing permafrost creates another feedback loop. Warming thaws permafrost, which releases greenhouse gases, which causes more warming, which thaws more permafrost. What makes tipping points so challenging for both science and policy is that they're inherently difficult to predict precisely. You can model them, you can identify the feedbacks, you can estimate ranges, but knowing exactly when a threshold will be crossed requires a level of precision that the system's complexity makes nearly impossible. It's like knowing that a bridge will eventually fail under increasing load, but not being able to say whether it'll be at 10 tons or 12 tons or 8. The uncertainty doesn't mean the risk isn't real. It means you can't wait for certainty before acting, because by the time you're certain, you may have already crossed the threshold. In 2008, a landmark paper by Timothy Lenton and colleagues in the Proceedings of the National Academy of Sciences attempted to catalog the major tipping elements in the Earth's climate system and estimate the warming thresholds associated with each. It was one of the first systematic efforts to map this landscape, and it identified about a dozen potential tipping points, ranging from ice sheet collapse to monsoon disruption to coral reef die-off. The paper was careful about uncertainties, but its central message was clear. Some of these thresholds might be uncomfortably close to the warming already committed by current greenhouse gas levels. And this brings us to the Paris Agreement, because the tipping point framework fundamentally shaped how the world thought about climate targets. When negotiators from nearly 200 countries gathered in Paris in December of 2015, the question on the table was deceptively simple. How much warming is too much? The answer they arrived at, holding warming to well below 2 degrees Celsius above pre-industrial levels, with efforts to limit it to 1.5 degrees, wasn't pulled from thin air. It was informed by precisely this kind of analysis, by the growing understanding that somewhere between 1.5 and 2 degrees, you start flirting with thresholds that could lock in changes that no treaty or technology could easily reverse. That was the logic. Not just that warming is bad, of course it is, but that there are specific thresholds in the Earth system where bad becomes irreversible, where the planet starts doing things on its own that amplify the problem regardless of what humanity decides to do next. The 1.5-degree target in particular was championed by small island nations, the alliance of small island states, who understood with painful clarity that for them, the difference between 1.5 and 2 degrees wasn't academic. It was existential. It was the difference between their countries surviving and their countries disappearing beneath rising seas. And here's what's worth sitting with for a moment. The Paris Agreement was, in a sense, the culmination of everything we've been talking about. Centuries of climate science, from Fourier's greenhouse intuition to Tyndall's gas experiments, to Arrhenius's hand calculations, to Keeling's relentless curve, to Manob's models, to Hansen's testimony, to the ice core revelations, to the tipping point framework. All of that knowledge, accumulated over nearly 200 years, funneled into a single political commitment. Nearly 200 nations agreeing, at least in principle, that the science was clear enough to act on. That's remarkable. It's also, as you might expect, more complicated than it sounds. Because the Paris Agreement is built on what are called nationally determined contributions, NDCs, which are essentially pledges that each country makes about how much it will reduce its emissions. And the thing about pledges is that they're voluntary. There's no enforcement mechanism, no climate police, no penalty for falling short. The agreement relies on a ratchet mechanism where countries are supposed to come back every 5 years with more ambitious targets, driven by a combination of peer pressure, moral obligation, and, ideally, the falling costs of clean energy making deeper cuts economically attractive. Whether that mechanism is working fast enough is one of the defining questions of our time, and the honest answer, as of the mid-2020s, is that it's not. Global emissions have continued to rise, though the rate of increase has slowed. The pledges made so far, even if fully implemented, would put the world on track for somewhere around 2.5 to 3 degrees of warming by the end of the century. That's better than the 4 to 5 degrees we were heading toward before Paris, but it's well above the targets the agreement set. And it's firmly in the territory where multiple tipping points become likely rather than merely possible. So let's talk about what's actually been happening to the climate, while all of this political machinery has been grinding forward because the planet hasn't been waiting for negotiations to conclude. The 21st century has been a masterclass in what climate scientists have been predicting for decades, and in some cases, things have moved faster than the models suggested. Take sea ice. Arctic sea ice extent has been declining for as long as we've had satellite records, since 1979. But the pace of decline has been stunning. The summer minimum, which occurs in September, has lost roughly 40% of its area compared to the late 1970s. In 2012, the Arctic hit a record low that shocked even researchers who'd been expecting decline. The ice that remains is thinner and younger, less of the thick, multi-year ice that used to dominate, more first-year ice that forms in winter and melts easily the following summer. Some projections suggest the Arctic could see essentially ice-free summers by the 2040s or even sooner. And this matters beyond the Arctic itself because of ice albedo feedback, that self-reinforcing loop where losing bright reflective ice exposes dark ocean water that absorbs more heat, which melts more ice, which exposes more water. It's one of the reasons the Arctic is warming roughly 3 to 4 times faster than the global average, a phenomenon called Arctic amplification. Then there's the heat itself. You've probably noticed this in your own life. The summers getting hotter, the heat waves more intense, the records falling year after year. 2023 was the hottest year in the instrumental record, and 2024 appears to have matched or exceeded it. The global average temperature is now about 1.2 to 1.3 degrees Celsius above pre-industrial levels. That might sound small, barely more than a degree. But remember, we're talking about the average temperature of the entire planet, land and ocean combined. Small changes in that average translate to enormous changes in extremes. A world that's 1 degree warmer on average is a world where heat waves that used to occur once every 50 years now occur once every 10. Where rainfall events are more intense because a warmer atmosphere holds more moisture, about 7% more for every degree of warming following the Clausius-Clapeyron relation, which is just basic thermodynamics, where wildfires burn longer and fiercer because vegetation dries out earlier and fire seasons extend. And this is where detection and attribution science, the fingerprinting work that Santer and others pioneered, has evolved into something genuinely remarkable. There's now a field called event attribution that can analyze a specific extreme weather event and estimate how much more likely or more intense it was because of human-caused climate change. When a devastating heat wave hit the Pacific Northwest in June of 2021, temperatures reaching nearly 50 degrees Celsius in Lytton, British Columbia, a place where 40 degrees would have been extraordinary. A rapid attribution study by World Weather Attribution found that the event was virtually impossible without human-caused climate change, not just made worse. Virtually impossible without it. That's a profound statement. It means the background conditions created by a century and a half of greenhouse gas emissions fundamentally altered what the atmosphere was capable of doing. Here's the thing about these attribution studies that I find really compelling. For decades, climate scientists were careful, maybe too careful, about linking any single weather event to climate change. The standard line was always, you can't attribute any individual event to climate change. And that was technically correct in a narrow sense, but it was also deeply misleading because it implied that climate change was somehow separate from weather, floating above it, when in reality every weather event now occurs in an atmosphere that has been fundamentally altered. The analogy people sometimes use is a loaded die. If you load a die so that sixes come up more often, you can't point to any individual six and say, that one was caused by the loading. But you can say with statistical confidence that the loading made sixes more frequent and that this particular six was more likely because of it. Event attribution science has made that kind of statement rigorous and quantitative, and it's changed the conversation. It's made climate change concrete and present tense rather than abstract and future tense. Now, while all of this observational evidence has been accumulating, the models themselves have continued to evolve. Remember Manabe's early work, that single-column model, then the Coupled Atmosphere-Ocean GCM. The descendants of those models are now extraordinarily sophisticated. Modern Earth system models include not just the atmosphere and ocean, but also land surface processes, vegetation dynamics, atmospheric chemistry, ice sheets, and increasingly, biogeochemical cycles like the carbon cycle itself. The models are run on some of the most powerful supercomputers on Earth, and they're coordinated through something called the Coupled Model Intercomparison Project, CMIP, which allows dozens of modeling centers around the world to run standardized experiments so their results can be compared. The latest round, CMIP6, involved over 100 model versions from about 50 groups worldwide, and the results fed directly into the IPCC's 6th assessment report, published in stages between 2021 and 2023. That report, AR6, as it's known, was in many ways the most definitive statement climate science has ever produced. The headline finding from Working Group 1 was stark. It is unequivocal that human influence has warmed the atmosphere, ocean, and land. Not likely, not extremely likely, unequivocal. That word was chosen deliberately. It means there is no remaining scientific doubt about the basic fact of human-caused warming. The report also narrowed the likely range of equilibrium climate sensitivity. That number Arrhenius first tried to calculate. The warming you get from doubling CO2 to between 2.5 and 4 degrees Celsius, with a best estimate of 3 degrees. That range has been debated for over a century, and it's remarkable that after all that time, after all the advances in modeling and observation, the answer is still broadly consistent with what Arrhenius estimated by hand in 1896. He got 5 to 6 degrees, which was a bit high, but he was in the right ballpark with pencil and paper and a lot of patience. But here's where the story gets both hopeful and sobering at the same time, because alongside the increasingly alarming science, something else has been happening. Something that even the most optimistic projections from a decade ago didn't fully anticipate. The cost of renewable energy has plummeted. Solar photovoltaic costs have dropped by roughly 90% since 2010. Wind energy costs have fallen by about 70%. Battery storage costs have declined by over 80%. These aren't incremental improvements. They're the kind of exponential cost curves that transform industries. In many parts of the world, building new solar or wind capacity is now cheaper than running existing coal plants, let alone building new ones. Global renewable energy capacity additions have been breaking records year after year, and in 2023, the world added more solar capacity than the total installed capacity of just a few years earlier. This matters enormously because for decades, the implicit assumption in climate policy debates was that reducing emissions meant economic sacrifice, slower growth, higher energy costs, reduced standards of living, and that framing made the politics nearly impossible because no country wanted to bear those costs unilaterally. But the clean energy revolution has started to flip that equation. Increasingly, the economic argument favors transition rather than opposing it. Countries and companies that move early on clean energy stand to gain competitive advantages, while those that cling to fossil fuels risk stranded assets, infrastructure that becomes worthless before the end of its expected lifetime. And yet, and this is the tension at the heart of the 2020s, the transition isn't happening fast enough. Not nearly fast enough. Because even as renewables surge, global fossil fuel consumption has remained stubbornly high. Oil demand hit record levels in 2023. Natural gas consumption continued to grow. Coal use, which many had hoped was in terminal decline, actually ticked upward in several years, driven largely by demand in Asia. The problem isn't that clean alternatives don't exist. They increasingly do, but that the scale of the global energy system is almost incomprehensibly vast. The world consumes something like 500 exajoules of primary energy per year, and roughly 80% of that still comes from fossil fuels. Replacing that infrastructure, the power plants, the pipelines, the refineries, the shipping fleets, the industrial processes, is the largest engineering project in human history. And it needs to happen in decades, not centuries. This is where climate science meets engineering in the most direct possible way, because the question is no longer whether the climate is changing or why. Those questions are settled. The question is whether humanity can engineer its way through the bottleneck fast enough to avoid the worst outcomes. And that question involves not just energy technology, but material science, grid engineering, industrial process redesign, agricultural transformation, and, perhaps most challengingly, the politics of coordinating action across nearly 200 sovereign nations with wildly different interests, capabilities, and historical responsibilities. There's a concept in climate policy called the carbon budget, the total amount of CO2 that can still be emitted while keeping warming below a given target. For 1.5 degrees, that budget is nearly exhausted. As of the early 2020s, the remaining budget for a 50-50 chance of staying below 1.5 degrees was roughly 200 to 300 gigatons of CO2, and the world emits about 40 gigatons per year. You can do the math. At current rates, that budget runs out within a decade. For 2 degrees, there's more room, perhaps another 1,000 gigatons. But even that requires emissions to peak very soon and decline rapidly thereafter. And this brings us to something that would have seemed like science fiction not long ago, but is now a serious area of research and increasingly of deployment. The question of whether, in addition to reducing emissions, humanity might need to actively remove carbon dioxide from the atmosphere. Because even in the most optimistic scenarios for emissions reduction, there are sectors that are extraordinarily difficult to decarbonize: aviation, shipping, cement production, steel manufacturing, agriculture. These so-called hard-to-abate sectors may continue emitting for decades, and compensating for those residual emissions may require what's called carbon dioxide removal, or CDR, and the approaches being explored range from the ancient and low-tech to the remarkably high-tech, and each one tells you something about how far climate science has come. From Fourier's quiet intuition about heat-trapping gases to a world where engineers are literally designing machines to pull those gases back out of the sky. Let's start with the simplest approach, the one that's been around for as long as there have been forests. Trees. Photosynthesis. You plant a tree, it grows, it absorbs carbon dioxide from the air and locks it into wood, roots, leaves, soil. Afforestation, planting trees where there weren't any, and reforestation, replanting where forests were lost, are the most intuitive forms of carbon dioxide removal. And they work. A healthy, growing forest can absorb several tons of CO2 per hectare per year. Multiply that across millions of hectares, and the numbers start to matter. But here's the thing. Trees are slow. A newly planted sapling takes decades to reach its full carbon-absorbing potential, and forests are vulnerable. They burn, as we've seen with increasing frequency in the American West, in Siberia, in the Amazon. A wildfire can release in days or weeks the carbon that took decades to accumulate. Forests are also limited by land. The Earth has a finite amount of suitable land for tree planting, and much of it is already spoken for. Agriculture, cities, ecosystems that shouldn't be converted to monoculture tree plantations. So trees are part of the answer, a beautiful and important part. But they're not sufficient on their own. Then there's something called BECCS, bioenergy with carbon capture and storage. The idea is elegant in a systems engineering kind of way. You grow biomass, crops, fast-growing grasses, trees, and that biomass absorbs CO2 as it grows, just like any plant. Then, you burn it to generate energy, but instead of letting the CO2 from combustion escape into the atmosphere, you capture it at the smokestack and inject it deep underground into geological formations where it can stay locked away for thousands of years. In theory, you've created a net negative energy source. You've generated electricity while removing carbon from the atmosphere. The problem, again, is scale. To make a meaningful dent in atmospheric CO2, BECCs would require enormous amounts of land for growing biomass, potentially competing with food production. The capture technology works. We know how to separate CO2 from flue gases, but the infrastructure for transporting and storing that CO2 underground is still in its infancy. As of the mid-2020s, there are only a handful of large-scale carbon capture and storage facilities operating worldwide, and their combined capacity is a tiny fraction of what would be needed. And then there's the approach that captures the imagination most vividly: direct air capture, or DAC. This is exactly what it sounds like. You build a machine that draws in ambient air, chemically strips out the CO2, and either stores it underground or uses it for something. The Swiss company Climeworks opened a plant called Orca in Iceland in 2021, capable of capturing about 4,000 tons of CO2 per year. They followed it with a larger facility called Mammoth, designed for roughly 36,000 tons per year. In the United States, the Department of Energy announced funding for regional direct air capture hubs, with companies like Carbon Engineering, now acquired by Occidental Petroleum, developing designs for plants that could capture up to 1 million tons per year. The engineering is real. The chemistry works. Most DAC systems use either liquid solvents or solid sorbents that selectively bind CO2 from air, then release it when heated, producing a concentrated stream of CO2 that can be compressed and stored. But here's the challenge, and it's a fundamental one that goes back to basic thermodynamics. Carbon dioxide in the atmosphere is dilute, about 420 parts per million, which means for every million molecules of air, only about 420 are CO2. Separating a trace gas from a vast volume of air requires energy. A lot of energy. Current DAC systems consume somewhere between 6 and 10 gigajoules of energy per ton of CO2 captured, depending on the technology. If you're powering that process with fossil fuels, you might emit nearly as much CO2 as you capture, which defeats the purpose. So DAC only makes sense if it's powered by clean energy: solar, wind, geothermal, nuclear. Iceland is an ideal location precisely because it has abundant geothermal energy. The cost, as of the early 2020s, is roughly $400 to $600 per ton of CO2 for direct air capture, though projections suggest this could fall to $100 to $200 per ton with scale and learning by doing. The same kind of cost curve that drove solar panels from impossibly expensive to astonishingly cheap over 2 decades. There's also enhanced weathering, which is a fascinating approach because it accelerates a natural process that already removes CO2 from the atmosphere, just very slowly. When certain silicate rocks, basalt for instance, are exposed to rain and atmospheric CO2, they undergo chemical weathering reactions that convert the CO2 into stable carbonate minerals. This is actually one of Earth's long-term thermostats, part of the carbon cycle that operates over hundreds of thousands of years. The idea behind enhanced weathering is to crush basalt into fine powder and spread it on agricultural land, where the increased surface area dramatically speeds up the reaction. Some studies suggest this could remove 1 to 2 gigatons of CO2 per year if deployed at massive scale, with the added benefit of improving soil health and potentially increasing crop yields, since the weathering products include nutrients like calcium, magnesium, and potassium. It's low-tech. It uses a rock that's incredibly abundant. Basalt covers vast areas of the Earth's surface, and the carbon ends up locked in minerals that are stable for geological timescales. The challenges are logistics and energy, mining, crushing, and distributing billions of tons of rock requires industrial infrastructure and energy, and the science of how quickly the weathering actually proceeds in real-world soil conditions is still being refined through field trials. And then there's ocean-based carbon dioxide removal, approaches that leverage the fact that the ocean is already the planet's largest carbon sink, absorbing roughly a quarter of human CO2 emissions. Some proposals involve ocean alkalinity enhancement, essentially adding alkaline minerals to seawater to increase its capacity to absorb CO2, similar in concept to enhanced weathering, but applied to the marine environment. Others involve cultivating kelp or seaweed in the open ocean, harvesting it, and sinking it to the deep seafloor where the carbon would be sequestered for centuries. These approaches are earlier stage, and they raise legitimate ecological concerns. You're deliberately altering ocean chemistry, and the marine ecosystem is complex and not fully understood. But the research is active and growing. Now you might be thinking, this all sounds speculative, or at least very early. And you'd be right to note that the total amount of carbon dioxide being removed by all engineered CDR methods combined, as of the mid-2020s, is on the order of tens of thousands of tons per year. Compare that to the 40 billion tons we emit annually. The gap is staggering. And this is why every serious climate scientist and every major assessment, including the IPCC's reports, emphasizes that carbon dioxide removal is a complement to emissions reduction, not a substitute for it. You cannot emit your way to safety and then clean it up later. The math doesn't work, the economics don't work, and the timelines don't work. Emissions reduction. The hard, unglamorous work of transitioning energy systems, electrifying transport, redesigning industrial processes, changing agricultural practices, remains the primary lever. But here's what's quietly remarkable about where we stand. If you step back far enough, if you take in the full arc of the story we've been following all through this journey, from Fourier sitting in his study in the 1820s, puzzling over why Earth is warmer than bare physics would predict, to Eunice Foote, holding glass jars up to sunlight, to Tyndall in his basement laboratory with his spectrophotometer, to Arrhenius grinding through thousands of calculations by hand, to Keeling watching that sawtooth curve climb year after year on his strip chart recorder in Hawaii, to Manabe writing the first climate model on punch cards, to the ice core teams in Antarctica pulling up cylinders of ancient atmosphere, to Hansen sweating in that Senate hearing room in 1988, to the negotiators in Paris in 2015. What you see is something extraordinary. You see a species that figured it out, slowly, imperfectly, with wrong turns and wasted decades and political interference and human stubbornness, but figured it out nonetheless. The basic physics was understood by the mid-19th century. The observational confirmation came in the mid-20th. The modeling matured by the late 20th. And by the early 21st century, the evidence was so overwhelming, so convergent across so many independent lines of inquiry, atmospheric measurements, ocean heat content, ice sheet dynamics, paleoclimate records, satellite observations, fingerprinting studies, event attribution, that the scientific question was, for all practical purposes, resolved. Think about what that means. Think about the sheer improbability of it, that a species of primates on a small rocky planet could develop the mathematics, the instruments, the computational tools, and the institutional frameworks to understand the behavior of an entire planetary climate system, that they could measure the composition of air trapped in ice 1 million years ago, that they could simulate the atmosphere on a grid and predict, decades in advance, the patterns of warming that would actually occur. Manabe's early models predicted polar amplification, and polar amplification is exactly what we observe. Hansen's 1988 projections, adjusted for actual emissions, have tracked remarkably close to observed warming. The models aren't perfect. They never will be, because the climate system is genuinely complex. But they've been far more right than wrong, and they've been right about the things that matter most. And so here you are, lying in the dark, at a moment in history that future generations will study with either gratitude or grief, depending on what happens next. The science is done, in the sense that the fundamental questions are answered. The engineering solutions exist, in the sense that we know how to generate clean energy, how to electrify most of what needs electrifying, how to begin removing carbon from the atmosphere. The economics are increasingly favorable. Clean energy is now the cheapest form of new electricity generation in most of the world. What remains is execution, deployment, political will. The messy, human, deeply imperfect process of actually doing the thing at the speed and scale required. And maybe that's the most fitting note to rest on, because this whole story has always been about that tension between knowing and doing, between understanding a problem and mustering the collective will to address it. Arrhenius understood the greenhouse effect in 1896, and here we are, more than a century later, still working through the implications. But the fact that we understand it at all, that's not nothing. That's actually remarkable. That's the product of thousands of careers, millions of measurements, centuries of accumulated insight, passed from one curious mind to the next, like a flame that never quite goes out. So let that thought settle. Let the weight of it be gentle rather than heavy. The atmosphere is doing exactly what the physics says it should do, and we know why, and we know what to do about it. And slowly, too slowly perhaps, but genuinely, the world is turning in that direction. Solar panels glinting on rooftops, wind turbines turning on ridgelines, electric buses humming through city streets, ice cores carefully archived in freezers, holding their ancient secrets safe, satellites circling overhead, watching, measuring, keeping the record. And somewhere, right now, a graduate student is staring at a data set, noticing something no one has noticed before, and feeling that quiet thrill that Fourier must have felt, that Foote must have felt, that Keeling must have felt, when the curve first began to climb and the planet started telling its story in numbers. The air you're breathing right now carries about 420 parts per million of carbon dioxide. Each breath you take contains molecules that have cycled through oceans and forests and volcanic vents and the lungs of creatures that lived millions of years before you. The atmosphere is old and patient and governed by laws that don't care about politics or quarterly earnings or election cycles. It simply responds to what's in it. And we know now with extraordinary precision what's in it and what that means. That knowledge is a kind of gift, hard-won, painstakingly assembled, and freely available to anyone willing to listen. You've been listening. And now, as the story settles into quietness, as the details soften and blur at the edges the way things do when sleep is close, just let it all be. The science holds, the atmosphere breathes, and tomorrow, the curve will tick up by another fraction, and somewhere, someone will be working on what comes next.